All right. So we'll break this up into three parts. All right. So the first part, we'll go through this problem together. It's an optimization problem where I want to solve the problem, develop the equations. Okay, that's a skill we've found a bit challenging that we want to develop some competence in. And particularly focus on how we can use the calculator to answer some of the later parts. Okay, so the calculator to support our answers. So that's the first part. In the second part, we'll do a tangent question and we'll look at how we can use our calculator to help us there. And in the third part, we'll just look at developing equations from the textbook. Okay, so when we did that exercise 15F, I said, let's skip over the equation part and focus on the calculator techniques. So in the test, right, you can expect the optimization question to look like this. There'll be four parts to it. Part C and D, you can just answer using those calculus techniques. That's what we were practicing. But part A and B, that's probably where we need to develop a bit of skill around finding the equation. So I'll go through about 5 or 6 up here, and one of those will be similar to the one in the text. Okay? So here we go. We've got farmer has 60 metres of fencing to make a pen. One wall will be the existing barn. So there's the barn on the farm. And explain why 2 lots of x plus y equals 60. So this will be something like 1 mark. It's as simple as saying the farmer has 60 metres of fencing and the sum of the 3 walls, x plus y plus x, is equal to 60. Okay, so to answer part A, farmer has 60 metres of fencing. And the 3 walls x plus y must add to 60 metres for him to use all the fencing. Okay, part B, show that the area is given by this equation. Well, the area here, right, is x times y. So the area of the pen is x times y. But here we have 2 variables. We've got x and we've got y. And whenever we're solving an equation, we need to isolate it to one variable. Fortunately, we do have another equation. We do have 2x plus y equals 60. So we have a relationship involving x and y. So we're going to take that, 2x plus y equals 60, and we're going to rearrange it to get y by itself. All right? We're going to have y is equal to 60, take away 2 lots of x. Okay, so we'll need that step. That's probably 1 mark, recognizing that we need y. And then the second mark is going, well, the area is x times y, and this is what y is. So we're going to take that and substitute it in here. X times, what's the y value? 60 take 2x. And so it expands 60x take 2x squared. Okay, so there's the area function. Okay, now from there, part C, find the dimensions that maximize the area. So we need to use those calculus techniques. This is the skill we were developing, right? Well, a maximum occurs when the first derivative equals 0. So we need to differentiate this function. So if this is the area, then A dash will be 60 take away 4x. Okay, and then we draw the sign diagram of 60 take 4x. You can make the manual argument if you want, all right? I'm not going to, because I said we're going to focus on how to use the calculator techniques, right? So, on my calculator, I've got my graph here, 60 take away 4x. Hang on, let's just graph the area function first. So even in the circumstance where we can't find the derivative, the area function is 60x take 2x squared. All right, can't see it, which means we need to zoom out. All right, so V window, And when you can't see it, I just zoom right out. Now for my x min, x is a length, so it has to be positive. So that means the lowest my x could be is above 0. So I'm going to set my x min as 0, but my x max, well, I know the dimensions are 60 meters, right? It has to be 60 meters the whole way around. So the largest it could possibly be is like 30, because it has to be x on both sides. So we'll put 30 there. And then for y is going to be the area, so we'll just crank that right up. You can go 1,000, you can go 10,000, something like that. And we can see nicely we've got the area function there. All right. Now this describes the area of this shape for any value of x. It tells you the area when x is 1. It tells you the area when x is 2. It tells you the area when x is 3. It tells you the value of x that provides the maximum area. You can just go g solve max, okay? Now it's the area function, right? So this is the x value that gives us the optimal solution. It's a function of area, which means on the y-axis we have the corresponding area. This is the maximum area. When x is 15, the area is 450, okay? So that's one way we can use it to check. The other thing we've looked at is graphing, option, calc, d on dx, okay? Graph the derivative of y1, close the bracket. All right, now I'm going to unselect the first function. So I'm only graphing the second function. I'm graphing the derivative of y1. I'm graphing the line 60 take 4x. All right, and you can see it's the equation of a line. This is where we can get the sine diagram from, right? Now, I draw the line there because it doesn't have negative values, okay? We can g-solve that root. What do you think it's going to be? 15. And we can see it is above the x-axis and then it is below the x-axis. So we go from positive to negative. This means we have a local max at x is 15. All right, so to find the dimensions then, we're going to have, the dimensions are 15 by y. What's the corresponding y value? Well, y equals 60, take away 2 lots of x. So if we do 60, take away 2 lots of 15, we will have 30. So that can be tricky to get the y value, all right? But we've got an equation for y, we've got the value of x, so we put that in, it tells us the corresponding y value. If x is 15, y is 30. Okay, so that's the answer to part C. And then the answer to part D, what is the maximum area? Well, 15 times 30 gives you that 450 we saw before. 450 meters squared, and then up here we should have a unit as well for meters. Okay, so there we've seen, what do we do? We in the first 2 parts, we're developing the equation. In the latter 2 parts, we're using calculus techniques, but we're sort of using our calculator to support us in that process, right? So you do need to know how to find the derivative, all right? So you get a mark for finding the derivative, and you get a mark for drawing the sine diagram, which you can get straight from the calculator. You do not need to make a manual argument for the sine diagram, as we've done in semester 1. Okay, so that's the first question. Next, let's do a tangent question, unless anyone wants to ask anything about that. Cool, I'll rub this out quickly. So let's find the equation of a tangent to y equals, let's just do x squared plus 4x. Take 1 at x is 2. Okay, so for a tangent, we need 2 things, right? We need the point of contact and we need the slope. We need the PLC and we need the slope. Now, ideally, all right, to get all the marks for a tangent question, you do need to do some of this manually, okay? You don't need to find the point of contact manually, but you do need to find the derivative function and hence the slope. So you get 1 mark for doing that part. But you can still use your calculator to help you to check it and to get the later marks. So let's see here. For the point of contact, we've got x is 2, and if we want the corresponding y value, all we're doing is putting that number into this function, right? Now, if we're going to use our calculator, what we would do is graph the function. So I'm going to graph the function x squared plus 4x take 1. I'm just going to delete the derivative I've got here, and I'll set my v window just to standard for now. Alright, pretty good view of it. That's what it looks like. Now we want the information when the x value is 2. So you've already got this setting turned on, hopefully, but if you press shift menu, there's the derivative. And I said we'll just leave it on. My calculator resets on the computer every time I turn it off and on, so you should have that turned on. And the way you'll check is when you trace along it, okay, it tells you an x value, it tells you a y value, and it tells you a slope value. Now we want to know the tangent when x is 2. So I'll go to x is 2. We've got the y value is 11, and the derivative is 8. All right, so we've got the point of contact, and we've got the slope. Sorry, I got those wrong. That one's 8. All right, so that's a pretty useful one. Plus 4x take 1. So have the derivative on, trace to that point, x is 2. All right, what we'll do next is we're finding a tangent. So what is a tangent? It's the equation of a line. Maybe I can just show you how you get the mark for using the derivative process quickly anyway. If we want to know the slope, we need to get the derivative function, 2x plus 4, and we want to know what's the derivative when x is 2, and you put x is 2 into the derivative function, right? 2 times 2 plus 4, 4 plus 4, you've got 8. Okay, so that's where the slope comes from. The derivative is the slope function. All right, so you're getting 1 mark there, you're getting 1 mark for getting the point of contact, even if you just use your calculator, and then you get 2 marks for finding the line. So let's do that. The equation of a line is y equals mx plus c. All right, we have a slope of 8, so that means m is 8. And our point of contact is x is 2, y is 11. So we'll put 11 where the y is, and we put 2 where the x is. So we've got 11 take 16, and we'll get a minus 5. Alright, I'll sketch it for you, show you how beautiful it looks. Crank y up so we can see where it touches. Why is it touching? 8x take 5, not 11. Alright, so there's the curve, and you can see the tangent there, touching there. Okay, really good. So that's one way we can use our calculator to help us with the tangent. With the normal, we would just negative reciprocal it, right? Okay, let's just go through a few from question 2 on finding the dimensions. So if we open our textbook to page 422, and let's go through question 2, question 4, and question 5. Yeah, can I go and look? Anyone else have a calculator issue?
I don't know what I did, but I must have pressed something.
Oh yeah, I said, what you do here, press enter, and press type, and change it to y equals. Parametric equation. Yeah. Just sing out if that happens again, but yeah, that's fine. That's done. So we said page 422, and we've got here, this one's going to be a little bit different, and we're not going to solve the whole problem. Let's just focus on developing the equation. We have a duck farmer wants to build a rectangular enclosure of area 100 meters squared. The farmer must purchase wire netting for 3 of the sides, as the 4th side is an existing fence. So pretty similar, okay, but different because we've got a specific area. Naturally, the farmer wishes to minimize the length of the fencing. All right, you want to use the least amount of fencing possible. The shorter sides have a length of x. Show that the required length of netting to be purchased is L equals this. Okay, so if we provide a sketch of it, we've got an existing wall or whatever, we've got the shorter sides are X, okay? If the shorter sides have length X, there's 3 sides, so we can call this Y again. And what we have is the area is 100 meters squared, right? So what this means is X times Y equals 100. Okay, so that's a relationship for the area. And the other relationship is that we have is for the length. The length, the perimeter of this shape is going to be X plus Y plus X. All right, that's 2 lots of X plus Y. Okay, so we're pretty close to the equation already, except we've got 2 variables. So that means we need to use this relationship and perform a substitution. If we want to get Y by itself, we write it as 100 on top of X. We've got a clear substitution for Y. We're going to take that and plug that in here. And so we'll have L is 2X plus 100 on top of X. Okay, which is the equation that they give us. Done, and then you go on to do the calculus techniques. All right, we'll move on to question 4. All right, so we got a box. Radioactive waste is to be disposed in a fully enclosed box of lead with a volume 200 centimeters cubed. The base of the box has dimensions in the ratio 2 to 1. So the base has dimensions in the ratio 2 to 1. So if this is X, this length here is 2 lots of X, right? And then we've got some other variable here, H, okay? The height of the box. All right, show that X squared H equals 100. Well, the volume of this box, right, is 2x times, so it's the base times the width times the height. 2x times x times the height, and the volume equals 200. So this would be 2x squared h equals 200. And we divide both sides by 2. That's going to cancel the 2, right? We have x squared h equals 100. So that's part A done. Part B, show that the inner surface area is given by this equation. The inner surface area. Now imagine it has a lid, fully enclosed lead box. So yes, it does. Okay, so if we think of the surface area, all right, so if you're standing inside the box and you have to consider the area of every surface added together. So we've got the base, all right, plus the top, and then we've got the 4 walls, right? We've got the front wall and the back wall, and we've got the sides. All right, so I'm probably writing it out in a fairly elongated fashion, but we've got the base, right? The base is 2x times x. So the base is 2x squared. The top has the same dimensions, right? The top is 2x times x squared. 2x times x, which is 2x squared. Okay, then we've got the front and the back. Now the front is 2x by h, and so is the back, 2x by h. 2xh. So the front 2xh, the back 2xh. And then we've got the right side and the left side, and the right side and the left side are both x times h, right? All right, so we've got 6 surfaces, the bottom and the top, the front and the back, the left and the right hand wall. So bottom and the top, front and back, and the left and the right wall. Okay, and we can collect that together. We can simplify that a fair bit. We've got 2 lots of x squared plus 2 lots of x squared. That's 4 lots of x squared. And then I've got here 2xh plus 2xh. All right, that's 4xh plus 1 lot of xh, 5xh plus another lot of xh. We've got 6 lots of xh. Okay, so that's an expression for the surface area, but there's two variables. We need to isolate one of the variables, and so we're going, what's another relationship we've got? Here, look, x squared and h. We can rearrange this to say h is 100 on top of x squared. And now we've got something clean to substitute right there where the h is. So we'll do that. And then we're going to have x at the top and x squared at the bottom. So it simplifies to 600 on top of x. All right, so that's finding the equation. That's what they've wanted us to find, done. And then you go on and do the calculus techniques. Find the derivative, draw a sine diagram, and you're off to the moon. Okay, and last one we'll do then is pretty similar to the tank one we did the other day. Any questions so far? All right, so we have a cylinder. Cylinder must have a capacity of 1 litre. Explain why the height is. Okay, so the volume of a cylinder is pi r squared h. Now, any equations that you're required, like if you're required the volume of a cylinder, or any complex equations, I should say, if you're required the area of a circle or something like that, you'll be given them. You're expected to know the volume of a rectangular prism, okay, length times width times depth, but that's probably all you're expected to know, really. If you need anything complex extra, it'll be provided for you. So, we've got this cylinder here. Explain why the height is 1,000. Very good. So we've got the volume is 1 litre, all right? Now that's not a useful measurement for us because we're given units in centimetres, all right? And 1 litre is equal to 1,000 centimetres cubed. All right, and again, if you require any of those conversions, you'll be given those as well. It's not an assumption we make, but you know that. And then you can see if we've got pi r squared, h is 1,000, we just divide both sides by pi r squared. And we have a relationship for h, right? Okay, then it says, show that the total surface area is given by. So, the surface area of a cylinder. Okay, let's develop this equation together. Let's derive this equation. Let me show you where we get this from. Firstly, if we have a cylinder, right, we have the top, and then we have the bottom, and then we have the walls going the whole way around. So the area of a circle, if we have a circle, it has area, pi r squared, and it has perimeter or circumference, 2 pi r. All right, so they're two formulas that we're going to use to derive the surface area formula. Now, we've got the top and the bottom, they're both circles. All right, so if we're making an argument for the surface area, we'd say we've got 2 circles. All right, we've got 2 lots, and the circles are pi r squared. That's the top and the bottom of the cylinder can here. 2 pi r squared. Okay. But then we've got this like part going the whole way around here, don't we? And so the way I like to describe this, hey Sal, if you think of a cylinder, here's what it looks like. Okay, we've done the top and we've done the bottom circle. What I'm going to do is get my scissors out and go chop, 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 chop. What is it? It's a rectangle. That's all it is. And this is the height of the cylinder. All right, you think? This length here is the height of the cylinder. And what's this length across the top? Circumference of the cylinder, okay? So that means the area of this rectangle part is the circumference times the height, okay? And the circumference of a cylinder is 2 pi r. And then we've got the height, okay? Now, we're not going to assume you need to derive that formula. We give you that, okay? All right, and then the only substitution that's required is that one in there. All right, we've got 2 variables. We're going to take it down to 1. 1,000 on pi r squared. And you can see we've got pi at the top and the bottom, so that will cancel. We've got r at the top and 2 of them at the bottom, so one of them will cancel. And that gives us the 2 pi r squared plus 2,000 on top of R. Okay, so that's quite tricky, right? Getting those marks. But then, okay, even if you can't get this part, it's okay, because you take that equation, you differentiate it, you draw a sign diagram, you answer the question. You can still go ahead and get those final marks. All right, so that's probably enough, I reckon. So we've gone through how to use the calculator a little bit there in the first part, and then we've gone through how to develop some of those equations. Any questions from you guys for the group? All right, I'll come see how we're doing individually, but let's use our time